We are here finishing off chapter 1. Section 1.3 is called Accuracy, Precision, and Significant Figures. It's called page 23, but on your PDF it's page 41. It starts off by talking about measuring mass. So there's a pan balance versus a spring balance. It talks about accuracy versus precision. One nice way I think some people look at that is this is a GPS. So the idea is that you're trying to find, using these radio waves that connect to satellites, your position, where the real center of the bullseye is your actual position, and there's 4 different measurements. If these are your 4 measurements that you see here, then that means that this is fairly low precision, but pretty accurate. If you look at the average of these 4 measurements, it's about in the middle. So we call that accurate. It's right, but it's just not super precise. Precise meaning a lot of decimal places, and accurate meaning close to the true value. It's also possible to be precise but not accurate. This is a smaller cluster of 4 measurements, but they're all wrong, right? They're all pushing you off in that direction. So it's not accurate, but the number of decimal places is higher or something. It's a more precise measurement. So the uncertainty kind of takes into account both of these things. If you have a very low uncertainty, we're hoping that the accuracy is good and also the precision is good as well. But really, uncertainty is what is used most often in science. We talk about an uncertainty. The uncertainty is this number, sometimes called delta something. So if you're measuring a quantity A, it'll have some units. Then the uncertainty in A is called delta A, another thing with units. So for example, if you measure the length of a piece of paper somehow with a ruler, you say it's 11 inches, you might say that your uncertainty is 0.2 inches. And then you'd write the length of the paper as 11 inches plus or minus 0.2. Then there's something called percent uncertainty, really important, which is just the fraction. So the fraction of the uncertainty divided by the value that you measure. And if you want to convert it to a percent, you can just multiply times 100. Okay, so next section is a very important one for your practicals. It's called uncertainties in calculations. So basic idea is that any time you make a measurement in the lab, it has an uncertainty, a plus or minus on it. But let's say you measure 2 things and want to combine them in some equation to get a result. Then the result has an uncertainty, which is then based on the uncertainties of your input values. So, and then this is the point where the book actually gets it wrong. They talk about this method of adding percents, where they suggest that, for example, if a floor has a length and width of 4 meters and 3 meters with uncertainties of 2 and 1% respectively, the area of the floor is 12 and the uncertainty is 3%. They just took 2 plus 1. So that's, not only is that not correct, it's not even a good approximation if the measurements going into the calculation have small uncertainties. So I can show this. I'll put a link down to this Google sheet, but basically the proper uncertainty is always found by adding the squares of the uncertainties, in this case the percent uncertainties when you're multiplying, and then taking the square root. This is something called adding in quadrature. So this is the real way to propagate uncertainties. OpenStax, this book is trying to give you this approximation where you just add. So if 20% plus 20% gives you 40%. Well, that's just wrong. The real answer is 28%, okay? If you're multiplying, this is maybe length times width. This is area of a triangle. But anytime you're multiplying or dividing, they give an example in the book of 1% and 2%. They're saying it's 3%. Well, the proper is 2.2%. So it sometimes kind of works if one of the uncertainties is extremely small compared to the other. Like if you have 0.1% versus 20%, well then, yeah, OpenStax's method of just adding them gives you the right answer, very close to the right answer anyways. But even just picking the larger of the 2 uncertainties seems to always give you a much better answer. So these are the percent differences between the approximate and the real. Honestly, in this course, why don't we just do the real thing? Because I don't think there's any real reason to dumb this down. Let's just do the uncertainties. There is an uncertainty in anything calculated from measured quantities. For example, the area of a floor calculated from measurements of its length and width has an uncertainty because the length and width have uncertainties. How big is the uncertainty in something you calculate by addition or subtraction? Well, here's the example. If the uncertainty in x is ux, so that you report x plus or minus ux, and similarly, the uncertainty in y is uy, then if you either add these numbers, x plus y, so z equals x plus y, or z equals x minus y, or z equals y minus x, the uncertainty in the result is the square root of the sum of the squares of the uncertainties of the two numbers. This is called adding the uncertainties in quadrature. So that's addition or subtraction. The rule for how big is the uncertainty in something you calculate by multiplication or division, in this case, the percent uncertainty in the quantity is calculated by the quadrature sum of the percent uncertainties in the items used to make the calculation. Okay, so to put it in an equation, you can do this instead of percents, you can just use ratios. So if z equals x times y, or x divided by y, or y divided by x, then the ratio of uz to z is equal to the square root of the sum of the squares of the ratios of the individual errors to their quantities. So, for example, if a floor has a length of 4 meters and the width of 3 meters with uncertainties of 2% and 1% respectively, then you can calculate the percent uncertainty this way. The percent uncertainty is 1% squared plus 2% squared. Take the square root, and you get 2.2%, not 3%, okay? So the area of the floor is 12.0, and expressed as an area, this is 2.2% of 12 meters squared is 0.264 meters squared, which we could round to 0.3 meters squared, not 0.4. So since the area of the floor is given to 1/10 of a square meter. So you'd say 12.0 plus or minus 0.3. So the book also gets the check your understanding question wrong. I'll just do it again. So a high school track coach has just purchased a new stopwatch. The stopwatch manual states that the stopwatch has an uncertainty of plus or minus 0.05 seconds. So the team's top sprinter 1 week got sprinted the 100 meter at 12.04 seconds. The next week, 11.96 seconds. Can we conclude that this week's time was faster? So the book kind of just waves its hands and says, no, that's even wrong. We can compute the difference of times as delta t equals, just take the difference. You get negative 0.08 seconds. That's how much time he beat himself by. So, or they beat themselves by. So, is 0.08 seconds significant? Well, assuming that the stopwatch manual reports the only or significantly largest source of uncertainty, and there's no additional uncertainty due to the human pressing the stopwatch button, which is a big if, but if that's true, then you can calculate the uncertainty in the difference. You just take the sum of the squares. You're doing a difference, so you just take the sum of the squares of the uncertainties and then take the square root. So each time has an uncertainty of 0.05, so 0.005 squared plus 0.05 squared, square root is 0.07. So that's the uncertainty of this difference. So the difference is negative 0.08 plus or minus 0.07. So I would say this is not quite consistent with 0. It's just sort of outside that 68% range there. So we can just barely conclude that this week's time is probably faster. So I might suggest to the authors that they change that solution. They just say, no, that's not true. So let's move on. Significant figures indicate the precision of a measuring tool that was used to measure a value. For example, 36.7 has 3 significant digits. There's the 3, the 6, and the 7. 3 indicating the tenths column, 6 indicating the ones column, and 7 indicating the tenths column. Special consideration is given to zeros. For example, in 0.053, we consider these first 2 zeros to be placeholders. They're just put there in order to indicate that this 5.3 doesn't mean 53. It means 5/100ths and 3/1000ths, right? So since you're forced to put the zeros there, this is considered to have two significant figures. But if you were to say 10.053, then all of a sudden it's the zeros are not placekeepers there, they're part of what you measure. This is actually a very precise measurement with a 1/10,000th of uncertainty. So this is 1, 2, 3, 4, 5 significant figures. So you got to be a little careful with the zeros. Also, the zeros in 1300, we don't actually know. They could be placekeepers, or you might really know that it's not 1301. It's not 1300 or 1299. It's really 1300. It's a question is whether or not this number's been rounded to 1300 or not. So a better way to write it is using scientific notation. 1.3 times 10 to the 3, that's the same as 1300, but we know that that has two significant figures. 1.300 times 10 to the 3, again the same, but now we know this has 1400 significant, it has 4 significant figures. And when you use significant figures in calculations, if you're multiplying two numbers, the result should have the same number of significant figures as the quantity having the least significant figures entering into the calculation. So what that means is that you have to round it. So for example, maybe you have the radius of a circle has 1.2 meters. What's the area of the circle? Well, 1.2 squared times pi gives you this on your calculator, 4.52, etc., etc., etc. I guess this, if you wrote that down, I guess it would be fine, but it's sort of indicating a little more precision than you have. So you round it to 2. So you just do 4 and the 5, and then the 2 rounds down, so it's 4.5 meters squared. So in a way, it's a little more honest to say the area is 4.5 meters squared than to say that it's 4.5238934. For addition or subtraction, the rule is the answer can contain no more decimal places than the least precise measurement. And last section is called approximation. This is just in physics and in this class, I think it's good, a good practice to try to guess answers even before you do the calculation. And I'll talk about this a little bit. Sometimes I call it a sanity check, but sometimes you have a feeling for how big an answer should be, and if your answer you calculate is not that, doesn't match with your feelings, then that could be an indicator that something's wrong. Maybe your calculation's gone wrong. And it's good to check these things by approximating. And that's it for chapter 1. There's a glossary giving you some of the terms we used. There's sort of a summary, which can be helpful. And then there's a bunch of problems and exercises. And when you look at problem set 1, I'll have a couple of suggested questions for you from the end of chapter if you don't want to do all of them. Okay, thanks very much. And when we come back, I'll start in on chapter 2. Bye for now.